All right. Hello, everybody. Welcome back to our next round of remote learning. I do have some good news for you. After this one right here, right now, there will be only one more that I put out there. That's going to come out next week. And after that, we will have a test in that last week on the school calendar. On that, since we are having a test, what I am trying to do is have some kind of Zoom or Google Meet review session. I know that we haven't done a lot of those, or any actually, but I want to at least do one and give you the chance before you take a test to ask me some questions. I know email is always not the best. You can get by, but definitely just being able to ask me that way is more effective. So I want to make sure we get one of those in. So that means you need to be looking at Google Classroom for a survey. I'm going to ask what times either do work for you or what times will not work for you, and do my best to be available for the most people possible. If there's a time that works for 100% everybody, I will absolutely pick that time. If there's a time that works for the most people, if I can get 80%, if that's the best we can do, then that's the time I'm going to pick. But yeah, just let me know. That way we can get that figured out and let you know what's going on. Okay. So today, what we're talking about is conservation of energy. We've been talking about energy for the last 3 weeks, and now we're going to talk about how it is conserved. It's kind of interesting. We'll see how that works. Okay, so just some quick review. I know some of this is just the same kind of information, just coming back at you, but really, it's foundational to this unit and going to be really important for like the multiple choice section of your test. Okay, energy is the ability to do work or cause a change in another object. Okay, for example, when you close a door, right? It's not moving and then you push on the door. So it's moving, and then because you pushed on it, it is moving. So you caused the door to change from not moving to moving, and so you gave it energy. Energy is the ability to do work, cause a change in another object. We talked about kinetic energy specifically, and kinetic energy is related to motion. Any object in motion has kinetic energy, so if it's moving at all, then it has kinetic energy. And the more velocity you have, so the faster you're going, the more kinetic energy you have. And so the flip side of that is if you're not moving at all, then you have zero kinetic energy. If you're not moving at all, then you have zero kinetic energy. Okay, we also talked about gravitational potential energy, and potential energy that is stored, and gravitational potential energy is stored in gravity. The more height equals more energy. The farther you are from the ground, or let's say you're holding something above a table, the farther out above that table that you are, the more energy you have. So more height means more energy for gravitational potential energy. For example, if you hold a water balloon off the back of the bleachers, but you don't let go, you're holding it, and it's above the bleachers, so it has the potential to fall. It will fall if you let go. So that is potential energy, right? The gravitational potential energy, right there. One thing that's pretty important is that both kinetic and gravitational potential energy depend on mass. More mass equals more energy. If you've been following along the last couple weeks, right? 2 weeks ago, we did the equation for kinetic energy. It was 1/2 mv squared. It's got an m in it for mass. And last week, we gave you the equation for gravitational potential energy. That was mgh, also has an m in it. So mass matters for kinetic energy, and mass matters for gravitational potential energy. The more mass you have, the more energy that you will have. Okay, so here's an important question. Can an object have both kinetic energy and gravitational potential energy at the same time? Is that possible? And the answer is yes. So what we're going to do is I already mentioned the example of dropping the balloon off the back of the bleachers. We're gonna break that down a little bit. Okay, we're going to analyze that and look at the different time intervals from beginning to end. Okay. So first, the balloon starts above the bleachers, right? Let's say our bleachers are 10 meters tall. We're holding our balloon above the bleachers. We have not let go yet. We are still holding on to this. Okay, so if we're still holding on, we have not let go. That means it's not moving, right? So its kinetic energy equals 0. It's not moving, so it has no kinetic energy. But it's 10 meters above the ground, right? It's got some height. So that means that it does have gravitational potential energy. Okay, so this is how things start. We're holding on but haven't let go yet. Now, what we are going to do is we're going to let go. And I want to look at a moment in time, the moment in time when it's halfway down to the bottom. So here's our water balloon. We've dropped it, so it's on its way down. It hasn't gotten to the bottom yet, though. It's only halfway there. Okay, so because it's only halfway there, it's falling. So it's moving, which means it has kinetic energy. Okay, so now halfway down, it does have kinetic energy. But also, it's still 5 meters above the ground. It still has some height. It doesn't have all the height that it had before, but it does still have some height above the ground, so it does have gravitational potential energy. So now if you didn't believe me up here at the top that my answer was yes, can it have both at the same time? Right here in the middle is all the evidence you need. The water balloon's moving, so it has kinetic energy, and it still has some height from the ground, so it also has gravitational potential energy. So in this middle picture, it does have both. It started out with only gravitational. Now it has both. And let's look at what happens at the end, right? So I want you to notice my water balloon has reached the ground, but it's still a water balloon. And I really like this example because a lot of times students like to think that, well, it's at the ground, so it's not moving anymore. The ground stopped it. Yeah, that's going to happen, but I'm talking about that like 0.001 seconds, that super small moment in time where it has gotten to the ground, but it hasn't stopped yet, right? This water balloon has not broken. I made my picture like that on purpose to show that the ground has not stopped or broken the water balloon yet. It got to the ground, but it's still moving. It has not been broken yet, okay? So because it's still moving, it has kinetic energy. Okay, and because we're looking at that super small moment in time where it's at the bottom, it has reached the ground, which means its height is 0. It has no height. It's at the ground, so it has 0 gravitational potential energy. Now it's at the ground. Okay, so it's got no gravitational potential energy there. So let's kind of summarize what happened here. We started out at the beginning. We didn't have any kinetic energy. All of the energy was gravitational potential energy. Okay. And then in the middle, we've got some of both. I'm not even worried about in this slide. I'm not even worried about talking about how much. Just the idea is we start out with only gravitational potential energy. In the middle, it has both. And at the end, it only has kinetic energy, no gravitational potential energy when it gets to the bottom. And we want to be making sure we're paying attention to where things are located in these pictures. First, it's at the top, not moving. In the middle, it's moving, so it's got both. And where does it only have kinetic energy? It only has kinetic energy when we're at the bottom. Okay, so we're going to continue to look at something that's a little bit similar to that. Let's see what our setup is here. We've got a skater that is on a half pipe, which is just a ramp, a U-shaped ramp. That's all it is. Okay, and he's going to start up here at the ramp. Near the top of the ramp, not exactly at the top, but near the top. Okay, so he's placed up in the air. He has some height above the ground, right? Yes, I know that there's a ramp in the way, but a ramp is slanted, and we all know what's going to happen if we let this guy go. He's going to fall. He's going to roll down the ramp, right? He is going to fall. So he has some height. So he has gravitational potential energy because he's got some height. Okay, he's above the ground. We have to let him go. So right now he's not moving. So his starting kinetic energy is 0, just like the balloon, right? Just like the balloon, he's starting up in the air, so he has gravitational potential energy, and he also starts out not moving, so he does not have any kinetic energy at the top. And let's watch what's going to happen, right? Let's see. So we're going to drop him here. I'm going to play it here. That's going to press play. And he starts to fall, right? He starts to fall. And just like with the water balloon, right? Halfway down, or about halfway down, not exactly, but partway down, He's got some kinetic energy and some potential energy. I'm looking at this chart right here next to the ramp. This green bar shows kinetic energy, this blue bar shows potential energy, and this yellow bar shows total. So the total is exactly right. Like if you have 10 cookies and your friend has 10 cookies, in total you have 20, right? You just add it up. So this yellow bar is if you were to take the green and the blue and add them up. You take the green and the blue, you add them up, and you get the yellow bar over here on the side, right? So we can see that we have some green, that's kinetic. We have some blue, that's potential. We're about halfway down. And so this matches up with what we were just talking about with the water balloon. That halfway down or partway down, he has some kinetic energy and some potential energy. Some potential energy because he still has height, right? He has not gotten to the bottom. He still has some height, so he's got potential energy. But now that he's halfway down, he's moving, which is why he has kinetic energy, because he's moving now. Okay, now let's look what happens at the bottom. Right, here's the bottom. He's gotten to the bottom. He's at the ground now, so he has no potential energy, but he is moving, so he's got kinetic energy. And you actually look at that. He's got a lot of kinetic energy. Okay, he's got a lot of kinetic energy, but because he's at the bottom, he's got zero potential energy, and that matches up with the balloon too, right? Like we did 3 pictures with the balloon. The last picture was the balloon at the bottom, and it was the same thing. No potential energy, but a whole bunch of kinetic energy because it's moving. Okay, so, and if we let him go, he's going to come back up the other side of the ramp, right? And so what's happening in the energy? It's changing back and forth between kinetic and potential, right? Potential, and then he falls, and it turns into kinetic when he falls. When he starts to go back up, he slows down, and it changes back into potential energy. And you can just see that it's just going back and forth, back and forth. What's really important, though, this is the main idea. The more interesting thing, though, is what's happening with the total energy. What is happening with the total energy, the yellow bar? So the green and the blue are going up and down, back and forth. But what's happening with this yellow bar? The total energy. It's not moving. So that means his total energy stays the same. It never changes. It can change what kind of energy it is. It's changing back and forth with the 2 kinds. But if you take the green and the blue and you add them up, you always get the same total. Always get the same total. It's not moving, okay? And that's a really important physics concept, and it's so important that I am going to box this up. Okay, total energy never changes. And that is true across all the sciences too. Chemistry, biology, the total energy of our universe cannot change. It can change form, right? Like when we burn wood, the word wood has chemical energy, and when we burn it, it changes into a flame that we can see. So that's light energy. But what do we also know about fire? It's hot. So it's got a lot of thermal energy too. So when you burn wood, you're just taking energy that the wood already has and just changing it into a new form, which is thermal energy and light energy. Okay, but the important thing is that the total never ever changes. Okay, so some of you might be thinking, though, this example is not realistic because he's just going to keep going back and forth up and down the ramp forever and ever and ever. And that's not realistic because what do we have in the real world? He will slow down and stop eventually, right? He'll start slowing down. What's making him slow down and stop? Friction. Okay, friction. Friction is in the real world. What does friction do? Friction turns kinetic energy into heat. If you don't believe me, just take your hands and rub them together really, really fast for a long time. It actually won't take a whole lot of time for you to start to feel, your hands will start feeling warm. They'll start to feel hot. You're generating heat. That's what friction does. It takes movement, right? Like when you rub your hands together, they won't get hot if you don't move them. You have to rub them together to get them hot. So friction takes movement, which is kinetic energy, and turns it into heat. And that is thermal energy. And that's actually why, I know I didn't talk about it before, that's why this chart has a red, it could have a red bar too, thermal. So as the skater goes up and down, we should see some thermal energy because as he moves, it should change some of that energy into thermal energy. So let's do that. I'm going to skip ahead in this video to that part. So here we go. We've started our skater, but now we're including friction. We're going to let him go, but now we're going to include friction. And just like I was saying, what does friction do? It turns energy, it's slowing him down, but what's happening to that energy? Where is it going? It's turning into heat, and that's thermal energy. So you see that this thermal energy bar is growing, right? And that kind of matches up with what we would see. Eventually, what's going to happen? He does not keep going forever. He slows down and slows down and slows down, and eventually he stops, right? And that matches what happens in real life. But that energy didn't just disappear. That's the most important thing for you to know. That energy, it seems like he lost energy because he was moving and then he slowed down to a stop. So he lost energy, and he did, but it didn't just disappear. It can't. You can't just make it disappear. It just changed kinds. That's all that happened. It just changed from kinetic into thermal energy. And eventually, thermal energy gets all of it, eventually, which is why we eventually stop if we were to let this go in real life, right? But I'm going to bring this back to what I said was super important, the total energy, right? So let's look at that again and watch what happens to the thermal energy. So this is the difference this time is we're including friction. We've already looked at what happens with the thermal. What happens to the total? What's happening to the total? So now we're including friction. But if you notice the yellow bar, it's still not moving, right? It's still total. It does not change. Total energy does not change. Okay, so now it's just that we have 3 bars to add up instead of 2. So if you add up the green, the blue, and the red, you add up all 3 of those, you would get the yellow one. Okay, so the total energy does not change. It's just which kind it is different at different points of time. It starts out with kinetic and potential and turns into thermal, but the total never changes. And it's so important, I'm going to write it here again. Even though friction is included, the total energy never changes. Okay, so I'm going to do a couple example problems here. This will be the last slide, and we'll be done. Okay, so example 1. A water balloon is falling from the bleachers. At one moment in time, it has 15 joules of kinetic energy and 30 joules of potential energy. What is the total energy of the balloon? Well, total just means to add them up, so that's all you got to do. 15 kinetic, 30 potential, add them up. 15 plus 30 is 45 joules. Boom, there you go. All right, let's do another one. Example 2. A rock is dropped from the edge of a cliff. At some moment during the fall, it has 60 joules of kinetic energy. How much gravitational potential energy does it have if the total energy of the rock is 80? Okay, so the total is 80. 60 of the 80 is kinetic. So whatever the leftover is the potential. What's the leftover? How much do I need to get from 60 to 80? 20 joules. You could also figure that out by subtracting. 80 minus 60. What is that? That's 20. Okay. So in the first one, we're figuring out the total. In example 2, I gave you the total in one piece, and you had to figure out the other piece. The 2 pieces have to add up to 80. One piece is 60. So the potential must be 20. All right, I got 2 more. Example 3. A supply package is dropped from a plane. It has 70 joules of potential energy just before it is dropped. And 2 parts to this question. The first part is how much kinetic energy does it have as it reaches the ground? And then part B is how much kinetic energy does it have when it still has 10 joules of potential energy? Okay, so there's a couple really important ideas going on here. Okay, so a supply package is dropped from a plane. It's not thrown from the plane, it's dropped. So that means it was not moving to start with, right? So if it's not moving at the start, it doesn't have any kinetic energy. The only energy it has is potential. And how much does it have to start with? It has 70 joules of potential to start with. And because there's no kinetic to add to that, that means the total is 70. Okay? At the beginning, the potential and the total are the same at the beginning because there is no kinetic. It's not moving. So we know that our total is 70. we know that our total, I should write that, our total is 70. Okay, and that will help us answer both parts of the question here. All right, so if our total is 70, and part A is asking how much energy does it have as it reaches the ground? Well, if it's at the ground, how much height does it have? It doesn't have any height. The height is 0. So if we're at the ground, that means we don't have any potential energy. The only energy that we have at the ground is kinetic, which means that kinetic and the total are the same at the ground. And if you don't believe me, go back to the last slide and watch the skater at the bottom. The kinetic and the total are the same. And when he's at the top, the potential and the total are the same. So if we're at the bottom, we're at the ground, kinetic and total are the same. So what's the answer to part A? It's 70. Okay, so 70 is our total. At the top, all 70 is potential. At the bottom, all 70 is kinetic. Okay, it's only split when it's somewhere in the middle. So part B is asking how much kinetic energy does it have when it still has 10 joules of potential energy? Well, this is kind of like example 2. We know that our total is 70. Now in part B, the kinetic piece is 10. So how much is the potential piece? 60, because 10 plus 60 gets our total as 70. But this part A, this is super important that the total at the top, potential and total are the same. At the bottom, kinetic and total are the same. All right, last one, example 4. A skater has 90 joules of potential energy just before falling down a half pipe. So just like the example we just did, 90 is our total, okay? Because we're at the top, and so that means potential and total are the same. The total is 90. Partway down, he has already lost 5 joules of energy to friction. How much gravitational potential energy does he have when he has 30 joules of kinetic energy? So we know that our total is 90. 5 of it went to friction, and 30 of it is kinetic. So now basically all it is this is like example 2, except now instead of only having 2 pieces, now we have 3 pieces. The friction piece of 5 plus the kinetic piece of 30 plus something, all 3 pieces have to add up to 90. Okay, so if I want to know just one piece, then just like in example 2, we've got to subtract. Start with 90, take away 5, and take away 30, and you get 55. 55 joules. All I did was start with my total. We had 90, take away 5 because 5 of it went to friction, and 30 of it is the kinetic piece. So what's left over for potential is 55. Okay. All right. Just want to give you a heads up where this is going. I focused on just the energy part for this week. So everything was in joules. We didn't have to use any of the equations that we talked about before, but that's what's coming next week. Next week really isn't anything new. It's just taking this stuff that I've talked about today, and it's just going to take an extra step, because instead of telling you the energy, I'll tell you the velocity or the height. But you don't got to worry about that till next week anyway. Okay, all of your homework and stuff for this week will be using these kinds of these problems right here. So we'll just worry about that next week. Okay, well that's all I've got for you guys. Hope everybody is doing all right. Stay positive. All right, keep pushing through. We're almost done. Just a secondary reminder that you should be looking on Google Classroom for that survey so we can figure out what time is going to work best to do some kind of Zoom review or Google Meet review. Okay, so that's really important. Make sure you answer that survey, and we'll get that set up so you can ask some questions directly. Okay, all right. With that, that's all I've got, and so take care, everybody, and we'll see you next time.